We've covered now since the beginning of this unit 3 of Newton's laws. The first law, Newton's first law, says an object at rest will remain at rest until an unbalanced force acts on it. Not a force, an unbalanced force. Or in other words, a net force acts on it. An object in motion will remain in motion until an unbalanced force acts on it. It's going to remain in motion specifically in a straight line at a constant speed until an unbalanced force acts on it. Good. Newton's second law also has two aspects to it. It talks about the acceleration of an object. Okay, Newton's first law, sometimes called the law of inertia, is talking about not changing motion, right? It's the tendency to resist a change in motion in Newton's first law. Newton's second law talks about the other end of it, the change in motion, the acceleration. And Newton's second law says the acceleration of an object is directly proportional to, in other words, gets bigger with the net force. So as the net force gets bigger, the acceleration gets bigger. As the net force gets smaller, the acceleration gets smaller. It's inversely proportional to, or in other words, inversely related to the mass. Bigger the mass, smaller the acceleration. And that should make sense to us, right? You push a smart car with a certain force, you push a semi-truck with the same force, and you're going to accelerate the smart car a lot more than you're going to accelerate the semi-truck. So the first two laws talk about the motion of the object. First, trying to resist motion, and second, talking about when it doesn't resist motion, talking about when there is a net force acting on it, what happens to it. The third law is a little bit different. Okay, this talks about the interaction between two objects, not the actual motion of one object. The third law talks about the interaction when one object collides or hits another object or pushes another object. And it says, and you guys have heard this a million times through your schooling, for every action, there's an equal and opposite reaction. We said yesterday that I like to state it in the way that's up on the board right now. If object A applies a force on B, then B applies an equal and opposite force on object A. Why do we like to say it that way as opposed to for every action, there's an equal and opposite reaction? Well, because if we state it for every action, there's an equal and opposite reaction, what we often do is forget that there's a second object. We draw a free body diagram. It looks like all the forces balance, right? There's an action force, there's an equal and opposite reaction force. They balance out, the net force is zero. But of course, that's not the case because they're acting on two separate objects. One of the forces is on object A, the reaction force is on object B. We've got a net force on both of those objects, which of course leads to acceleration, which takes us to a Newton's second law analysis at that point. We said yesterday that Newton's third law always applies. There are zero exceptions to that rule. Zero. And one of the ones that people think of a lot is when an object doesn't stop. So let's say we throw the rock through the window like we talked about yesterday. The object doesn't stop. The rock keeps going through the window. The glass breaks. Newton's third law still applies? Yeah, we established yesterday that it does. Okay, in the end, if the rock applies a force of 30 newtons to break the glass, then the glass, while it's still in contact with the rock, must apply a force of 30 newtons back on the rock. So why does the glass break? Because the glass is weak. The glass is weaker than the rock. Okay, 30 newtons may be enough to break the glass. 30 newtons isn't enough in that case to break the rock. 30 newtons may be enough to break the glass. It may not even be enough to stop the rock. The rock may keep going right through the glass. It's probably going to slow down the rock, okay, but depending upon the mass of the rock, right, now it's going back to Newton's second law, depending upon the mass of the rock, it may not slow down all that much. It may not decelerate at that high of a rate. Let's give a couple examples of action-reaction forces here, okay, the whole Newton's third law thing. A couple of the examples that we talked about yesterday, first of all, okay, we kick a soccer ball. Okay, what's the action force? What's the action force? What's the force that we do? Kick the ball, right? The force of your toe on the ball, the force of your foot on the ball. What's the reaction force? The ball kicking you back, the force of the ball on your foot. Okay, when you kick the bedpost, we talked about that one as well. Okay, when you kick the bedpost, okay, there's the action force is the force of your toe on the bedpost. And the reason your toe gets hurt, right, is because the bedpost kicks you back. the force of the bedpost on you. What about something that's a little less, I don't want to say violent, because kicking a soccer ball isn't particularly violent, but a little less of a collision and a little bit more smooth of an interaction, like throwing a ball. Maybe I'm on ice, standing on ice. Okay, it's almost frictionless, not entirely, but almost frictionless. If I throw a ball forward, okay, what's the action force? Yeah, my hand pushing on the ball. Good. What's the reaction force? The ball pushes on my hand and therefore ultimately my body, right? So what happens when you throw a ball, a heavy ball on a piece of ice? Well, the ball goes forward and you go backward. Which accelerates more, the ball or you? Which has a higher rate of acceleration? Okay? Whatever weighs more or whatever weighs less. Yeah, generally that's probably going to be the ball that weighs less than you, right? But it's possible that it could be more, especially if it's a kid throwing it, right? Generally, though, we're not, if we weigh less than the ball, we're probably not strong enough to actually throw the ball, right? Probably. In the end, the forces are the same every single time, but one of them is going to probably have a higher mass, and that one with the higher mass is going to accelerate at a lower rate. Again, we're kind of tying in Newton's third law with Newton's second law here right now, right? The forces are the same, but the accelerations are dependent upon the mass. So if the force is the same, the one with the higher mass will have a lower rate of acceleration. Here's another one. What's the action-reaction force here? An airplane, a jet airplane, not a propeller airplane, but a jet airplane flies through the air. Okay, clearly it's propelled forward, right? What's the action force? It's a tough one. What's the action force? You guys know, right? Everybody knows at some level that something's got to push this airplane forward, otherwise it's not going to go forward. Tying it in with Newton's first law right now, right? If nothing pushes it forward, it's going to remain at rest, right? Fall out of the sky. So what pushes it forward? What's the action force here that pushes this airplane forward? Yep. Well, let's answer my question first, okay? And then we'll take a look at that. Okay, it's a good question, but let's take a look at the answer to my question first. You need to be more specific on that. No, we don't need necessarily the geometry of the engines. Anybody else? Go ahead. The wings in the air hitting each other. The wings are what keep it up. Okay. You guys learned about this, I think, in grade 6. You learned did a flight unit. You guys remember that? There's something called the Bernoulli Effect. Do you remember that? An airplane wing is shaped like this. The air flies, or the air approaches. This is the front end of the airplane wing. As the airplane wing cuts its way through the air goes below the wing, and it goes above the wing. It has further to travel above the wing. So in order to go around the wing, above the wing, it has to travel faster. When the air travels faster, it creates a low pressure zone, a low pressure area. And that low pressure area causes the wing to be sucked up. And if the wing is sucked up, and the airplane that is attached to the wing, then the airplane gets sucked up with it. So the airplane is literally getting sucked up into the air due to low pressure. Kind of like when you're in the shower. Every once in a while, you notice you're in the shower, and the shower curtain just kind of gets sucked in. Ever notice that sometimes? If there's not a weight on the bottom of the shower curtain, it gets sucked in. Why? Because as that water goes past the shower curtain on the inside, it creates a low pressure zone inside the shower and sucks the shower curtain in. Okay? Usually you have weights on the bottom of your shower curtain so that it kind of prevents that from happening. Okay? It's the low pressure zone here that sucks the airplane up. It's the wings that suck the airplane up, but it's not the wings that propel it forward. Yep. Uh, no, it's because the air molecules on the bottom are moving slower than the air molecules on the top. Um, it's the speed of it that matters here, because because these guys are moving faster up here. That's what creates the low pressure zone, which creates the lift force. The thrust of an airplane, which is that forward force, is created by the exhaust, right? You create an exhaust as you burn fuel, right? Okay? You burn fuel, the exhaust goes out the back. The airplane, in fact, pushes on the exhaust out the back of the airplane. What does the exhaust do to the airplane? The airplane pushes the exhaust backwards. The exhaust pushes the airplane forwards. If object A applies a force on object B applies an equal and opposite force on object A. I was kind of waiting for this answer. It's a wrong answer. Nobody gave it to me. That's good. But I was waiting for this because usually this is what I get. The exhaust from the airplane pushes on the air, and the air pushes it forward. Right? What's wrong with that? You need air to fly. Right? You need air to fly in an airplane because you need oxygen in order to burn fuel. But besides that, and you also need to create this low pressure zone above the wing, and if you don't have air going above the wing, then you can't have a low pressure zone. Okay, but besides that, the air has nothing to do with the thrust of the airplane. Nothing. Okay, the airplane could be thrust forward if you could burn the fuel. The airplane could be thrust forward even if there was no air, because in the end, it's the airplane pushing on the exhaust and the exhaust pushing back on the airplane. Picture this. It's a rocket ship. Okay, you're out in space. There is no air. How does the rocket ship get propelled forward? You can't push on the air and the air pushing back on the exhaust, right? The rocket ship pushes on the exhaust and the exhaust pushes back on the rocket ship to propel it forward. So how do you control a rocket ship? Right? We can control an airplane by changing angles of the wing and so on, but that's all dependent upon air. Right? That's all dependent upon air. How do we control a rocket ship? How do we turn it? Yeah. Yeah. You essentially, I don't know how many engines a rocket would have, but you'd thrust out of one side. It's thrust out of, say, the right side, then you're going to turn to the left. If you thrust out of the left side, right, you're going to turn to the right. Why is that the case? Well, because the exhaust, the ship pushes back on the exhaust on the right side, and then the exhaust on the right side pushes back forwards on the ship on the right side, which of course is going to cause it to go faster on the right side than the left side, which is going to mean it's going to turn to the left. That make sense?